this recording. I'm sharing my screen. Hopefully not on mute. You've got your test back. It wasn't great. That's okay. I did say that I would mark it very hard to clear up any bad habits for the final exam. Of course, the final exam, there's no more learning opportunities. I mark way nicer on the final exam. Okay, so don't worry. But I do want to kind of clean up any bad habits before the final exam, right? And so I feel like the average for test 2, and you're not going to like this, was about 55%. That's a pass. I know, not very nice. So then what are these p-values, do you think? What's my main concern when I use 2 versions? A huge concern for me would be if there was a difference, a significant difference in the grades on the test versions, right? Version 1 versus version 2. And so here, what's my null hypothesis? The mean for version 1 is the same as version 2. What's my alternative hypothesis? Mean for version 1 is not equal to mean of version 2. I don't care which direction. If they're different from each other, then I'm very concerned, right? What does this mean? A p-value for the overall grades of 0.24 means I do not have enough evidence to reject H0, and I breathe a huge sigh of relief, because otherwise I'd be in trouble. Right? Because then I can say, well, they're not significantly different from each other, and that's a good thing for me, right? Where do I get into some deep waters? For some reason on question 3, we're kind of close to having a significant difference. Now, this is kind of a nice opportunity to bring up, if you just do a bunch of tests, right? Sometimes just by random chance alone, you will reject the null hypothesis when you shouldn't, right? And so I'm not concerned about this, because overall, a p-value of 0.822, they're basically the same. And even 0.2, this one's just kind of a fluke. And of course, I looked at them because that's initially a concern, but not really. Yeah. So kind of interesting. Now you know what I'm talking about. Not significantly different. And on Moodle, I posted it in the test 2, which is last week, obviously, or I guess the week, who can remember? I don't know. Week 11, I posted blank versions of each of the versions, version 1, version 2, and then as well as the solutions, of course, for each of them. Now, at the end, you just have to do a little fire drill, figure out what type of question you have, and then if it's a one-sided or a two-sided test, right? Those are all important things. But then in the solutions, I just have kind of complete brief solutions as well. So if you wanted to use those are obviously questions that you could do for practice. And so you have those brief solutions there. So you can check your work. Okay. I cheat a little bit because I use software to find the p-value, right? They're brief solutions, but just to get a general idea. Okay. So you've got those to practice from, right? Those will be good. And then, any questions about the test before we keep going? Not here, not now. That's all right. So, last day, we introduced regression, right? Which is kind of a lighthearted topic to end on. And so we're fitting a least squares regression line. And I said for Thursday, find this least squares regression line. And I'm going to copy this up here. Oops, here. Because now we are on Thursday. So now it's time to do it. Time to pay the piper. I'll delete this slide though. Delete. Good. Okay. All right. Let's grab from the formula sheet the formulas that we're working with. We're just about to wrap up the entire formula sheet, if you can believe that. Oh, and before I forget, I posted, I posted the last of the assignments and the last of the labs. There's a bonus assignment and a bonus lab available as well. And so now you have everything. And I think I made all the due dates Sunday, April 14th. Okay. And so, because I want you to have them wrapped up before the final exam on the 19th and have questions for me before then. Yes.
The lab you posted is the last lab, and then the assignment you posted, is that the last assignment?
It
So
is.
both those are the last.
Yeah.
No more assignments for last.
If you cross those off your list, you're gravy.
Okay.
Yeah.
Perfect.
Let's have a look here. So up here, let me just confirm. So for the labs, there is a lab 10, which is on simple linear regression. Simple just means that we only have one explanatory variable. And then I made a bonus lab. If you want to, if you missed a lab or whatever, and you want to make up that grade, you can do the bonus lab on multiple linear regression, which means that you have more than one explanatory variable, but it's just an extension of what we're doing. So that's why it's a bonus. And so you can do that one or not. It's set to drop your lowest lab grade. Same thing for assignments. Where is it? Here. Once you do, so I posted a bonus assignment for more than 2 means is in ANOVA, and there's a link to a video that you can watch to do that assignment. It also links to an old version of the formula sheet because we don't have ANOVA formulas on our formula sheet. So I would check that out. And then assignment 16, last assignment. Whee! It's happening, guys. It's really happening. If you can believe that. I cannot. Okay, let's see here. Maybe I'll give myself a little bit more room. So what we wanted to do, and what you will have to do on the final exam, is you will have to calculate the slope, calculate the intercept, and build the least squares regression equation or line. Oops, there. From your formula sheet, the least squares regression line is this, right? And we talked about this last day, and so now we're last day we went from the angle of here's a line. Now what does it do? How are the residuals behaving and all that kind of fun stuff? And then today we're actually going to build this line using summary information like this. Okay. Couple of notes on the final exam. I don't tell you which one is the X and which one is the Y. In fact, one of the parts that you have to answer is what is the response variable, and then you have to know that that's your Y, right? And what is the explanatory variable, and you have to know that that's your X, okay? And so then this information could be given as a blurb, right? Just in a sentence. And so it's not always laid out this neatly, but you'll have all these pieces of information, right? And so what does this mean? Well, we know that this is your y-axis and this is your x-axis. And so the response variable in this case is the percent in poverty. which it has some average, right? It's numerical data, so I can calculate the average of y, and I can calculate the standard deviation of y. Same thing for the percentage of high school grads. I can calculate the average of percentage of high school grads across the states, and I can calculate the standard deviation of the high school grads. And so I use these little subscripts only to denote that one is the standard deviation of X and the other is the standard deviation of Y, right? That throws people off when they see this. They think SX must be something different, but it is just the standard deviation of X, standard deviation of Y. Okay. And we're told the correlation is negative 0.75, right? Remember, the correlation, as a little review, goes between -1 and +1. As we move out towards 1 in either direction, right, positive or negative, right, then it gets stronger and stronger. So here we have a strong negative linear relationship, right, because the correlation only applies to a linear relationship. Okay, so we want to build this line, right? Y hat is B naught plus B1 times X. And so B naught is the intercept and B1 is the slope. And we talked about it last day. We said, okay, there are hints, right? B1 is the slope. It says so, right? So there's no reason to get tripped up about that, right? With the slope of B1, which is what? It's the correlation times the standard deviation of Y over the standard deviation of X. You want to be careful that you haven't mixed those two up, right? Because if SY is 2 and SX is 1, 2 over 1 is 2, but 1 over 2 is 1/2, and that is going to make a huge mess, right? So you want to be really careful here. The standard deviation is spread. You can't have negative spread. And so the standard deviations are always positive. And so the only way that we can get a negative slope is through the correlation, right? And so, but we have these three pieces, right? It's given in the table. And so we can find the slope. And then once we have the slope, we need to find the slope first, because if you tried to solve for B0, which is natural, right? It's the first thing that appears in the formula, so why not? But then when you try to solve for it, you hit a roadblock and you think, oh, I need to solve for the slope first, right? So it'll happen naturally, okay? But the y-intercept we find by using the average of the y's minus the slope that you found times the average of the x's. Obviously, if you messed up your calculation for the slope on the final exam, I'll follow through. So even if you have to use the same slope that you found. It'd be very weird if it changed, right? And so as long as you follow through with whatever you found previously, I'm happy, okay? And so then you use your slope times the average of the x's and then subtract it from the average of the y's. And then we talked about the residuals. I'm not going to test you on the residuals on the final exam, but there is an assignment question that kind of talks you through residuals, makes you find residuals and that kind of thing. Okay. Nothing to it but to do it. Here we go. Oh, B1. Nice try, Emily. First, I'm going to solve for the slope. B1 is R times SY over SX. I encourage you to write down the formula that you're about to use, because that's where, if I see that you wrote it down wrong, but then you followed through, that makes more sense to me, right? I'm not as concerned about that. And so it's always good to write out what you're about to do before you do it, right? Otherwise, it's hard for me to decipher. You really want to hold my hand for when I'm marking your final exam, right? And so let's see here, negative 0.75 talk me through everything that you're doing, right? There's no harm in that. SY, here it's given explicitly as 3.1. Otherwise, you'd have to figure out, okay, which one is my X, which one is my Y, and what are the means and the standard deviations. But in this case, they're given 3.1 over 3.73. And I have, where is it? I had a screenshot. Maybe this one, I think. Yeah. So B1, the slope, I called it M here and B here, just from MX plus B, right? Because if I use the S and I for the intercept, I is a special value, so I wasn't allowed to use that. So then I reverted to MX plus B. But B1 is going to be roughly negative 0.62. Okay. I'll just round to 2 decimal places here. I want you to try to keep all your decimal places until the end. But like I said, when I'm marking your work, I will follow through, right? So you'll get a slightly different answer if you use the rounded value of the slope when you calculate the intercept, right? Versus keeping all the values, which is what I did. So next thing I want to do is find the intercept. Y bar minus M, oh, I guess it's not M, B1 times X bar, which is Y bar is the mean of the percent in poverty, 11.35, minus negative 0.62, I kept all the decimal places, times, I need a little bit more room here. I'm trying to keep it on this page, but it's hard. Times 86.01, the mean of the x's. And I find that B0 is roughly 64.96, which means that the least squares regression line, Y hat, is 64.96 plus negative 0.62, which is going to turn into minus 0.62 times X. I'll highlight that because it's squished on the bottom, and I'll add a page. So here, Y hat is 64.96 minus 0.62 times X. The goal of building this line was to predict values of Y, right? And so Y hat is the predicted percent in poverty, and X is the percent high school grads. So what we could do is we could write poverty hat, right? Anything with a hat over it means it's a predicted value. In the regression case, right, is 64.96 minus 0.62 times percent high school grads. However you want to write the equation is fine by me. I just find that this way might make it a little bit more helpful, right, in terms of interpreting the slope and the intercept, which is something that we'll have to do, that we're going to talk about next, or also predicting the percent in poverty, Okay, and so we've got the slope, we've got the intercept. Those are each questions on the final exam, I guarantee it. Okay, so a typical layout, which we'll talk more about next week for a regression question will be, okay, tell me what the response variable is, what the explanatory variable is. I might give you a scatter plot and ask you to describe the relationship, right? Strong, positive, linear relationship, that kind of thing. And then calculate the slope, interpret the slope, calculate the intercept, interpret the intercept. So these are all parts, I don't know, A through whatever. So many parts. So many parts. Okay. So we need to be able to interpret the slope and the intercept. Okay. In case you haven't felt it yet, stats is not so much math, but more kind of English and being picky about language and that kind of thing, right? So the math here is not hard, right? And so that's a relief to a lot of people who don't like math. But then we're stuck doing this tango with all the language components, right? And so that takes getting used to. And so what I want you to do, just like we've been memorizing the interpretation of the confidence interval and memorizing potentially the interpretation of the p-value in your conclusions, right? I'm going to give you the bare bones definition of the slope and the intercept, and then it's your job to apply it to the specific question, right? And so let's start with reminding ourselves of the general layout of the regression line, regression equation, and the slope, which is B1. I start with the slope because I make you calculate the slope first. Not trying to set you up or anything. And so the slope is a little bit more far-fetched than the intercept, and so that's why I'm starting here. But the slope, by definition, or interpretation of the slope, is for each unit increase in x, right? So as x goes from 1 to 2, for example, then the predicted value of y is going to increase by the slope amount, okay? And I use the term increase always, just because I don't want to get tripped up on a negative decrease, which is an increase, right? And that kind of thing. And so I always use the term increase, and I'll highlight what I mean in a second. And so the slope is for each unit increase in x, for each unit increase in x, we expect a B1, so a slope increase in the predicted value of y, and I'll just call it y hat, in the y hat, which is the predicted value of y. Just as a note, regardless of whether B1 is positive or negative, I always say increase, and I encourage you to do the same, right? Because if you have a negative 0.62 increase, that is a 0.62 decrease, but then you have to remember to remove the negative. Otherwise, a negative 0.62 decrease is actually a 0.62 increase, and you can see how that would make a real mess. So you want to stick with just whatever the slope is, increase. Okay. And maybe I'll say, regardless of whether B1, so the slope is positive or negative, I always say increase. All right. So just as an example, a negative 0.62 increase is a 0.62 decrease versus a negative 0.62 decrease is a 0.62 increase. Barf. So don't get stuck down that rabbit hole. Just always say increase, even if it sounds a little bit wonky. Okay. So if you just say a B1 increase, that's always going to be safe. Okay. As long as you keep the sign on there, of course. So for our example, B1 was negative 0.62. So what would we say? Applying this definition, right, and using this equation as your as kind of a training wheels, right, just kind of guiding you in the right direction, right? And it's really important that you have for each unit increase in X, right? Because it's not just as X increases, then the Y hat increases by this. It has to be for the unit increase. And so we would say for each unit increase in percentage of high school grads, oops, not period, right? You have to replace the X, you have to replace the B1, and you have to replace the Y hat. So for each unit increase in percentage of high school grads, we expect a negative 0.62 increase. It's a percentage, but I don't care about units. Don't tell your chemistry and biology professors if you have them. I don't care about units that often. So we expect a negative 0.62 increase in the predicted percent poverty, right? Y hat is the predicted percent poverty. Yeah. So that's what I would expect to see as your interpretation of the slope. Okay. For part marks, only part marks though, you can just give me the general definition, right? That's safe. It's not completely right, but I'll give you half marks. It's pretty good. It's just a memory game at that point. And anyone can play that game. Okay. How about the intercept? Like I said, the intercept is a little bit easier to remember because the intercept is B0. If I wanted to isolate B0 somehow, what could I do? I could let X be 0, right? And so at X equals 0, then B0, your intercept, is the predicted value of Y, right? So just using this equation to guide me there. So the intercept, which is B0, the B0 is the predicted value of Y, or Y hat. That doesn't look like a hat there. B0 is the predicted value of Y when X is 0. Okay. Again, when X is 0 is a key component of this interpretation, right? It's not always the predicted value of Y. It's only the predicted value of Y when X is 0. So for us, in our example, B0 was 64.96. Again, in percent, but that's okay. So we would say 64.96. And if you want, you can add the percent, but I'm not going to, just to keep it nice and bare bones. And so 64.96, because of course I need to replace the B0, Y hat, and what X is the predicted percent poverty when the percentage of high school grads in a state is 0. Okay. I don't want to add a page here because it's on the next slides, but a follow-up question would be, well, sometimes the intercept is meaningful and sometimes it's not. Do you suspect that we'll have a state where the percentage of high school grads is 0? We can look back at our scatter plot, our original scatter plot that we were given. These percentage of high school grads, so our data only goes between roughly 75 and 95% high school grads, right? And so the problem with lines and the beauty with lines is that it keeps extending to negative infinity, positive infinity, right? But it's only useful for this range of X, right? And so we could use this line to make further predictions for the predicted percentage in poverty if the percentage of high school grads is 5, right? But outside the range of this data that we built this line using, right? Our sample will only span the values of X between 75 and 95. So it's only going to give reliable predictions in this range, okay? And so when we use the line to predict outside the range of the data, and I'm just going to snag a copy of the scatter plot so we can talk about it. It's called extrapolation, okay, versus interpolation when you're predicting inside the range, but that's not a concern. In fact, that's the goal. But let me add a page. I said I wasn't going to, but then I did. Oh well. Just a fact. An LFF, a little fun fact. I haven't done very many LFFs this term. A little fun fact is that lines, of course, extend from X equals negative infinity to X equals positive infinity. Lines extend from X equals negative infinity. Can't get to there, so the equals kind of weird. But you'll forgive me, I think, to X equals positive infinity. All right, that's just how lines are. They just keep going and going and going. Okay. However, whoops. We will only have reliable estimates from this line, right? If we're using values of X that's in our data. Okay. We will only have reliable, and I said estimates, but I'll call them predictions, and they're the same. We will only have reliable predictions when using values of X in the range of the data. And I'll say that we use to build the line. So here, let's say roughly 75 to roughly 95, there's a little bit of wiggle room, right? But so for us, we only have reliable estimates within this range, okay? We can use the line outside there, but we would have to add a little note saying, hey, I'm extrapolating, and so my estimate isn't very reliable. So one of the terms that I need you to know, I guess, is extrapolation. I'll even highlight it. And the number of times that I've seen on the final exam, it's that word that I can't remember, where we use the line to predict outside the range of our data. And I know you mean extrapolation, and that's fine, right? It's the concept that I'm after, okay? But extrapolation is using the least squares regression line to predict values using values of X outside the range of our data. Depending on how much math you've done, right? Me saying range might be a little bit irksome, right? Because what is the range? The range is technically the y-axis, right? I should be saying domain, but it doesn't really work that way. And so in stats, we just say the range of the data, meaning the X values. That's confusing, I guess. But now you know. Use it. And so this means that the intercept, right? So because the line extends from negative infinity to positive infinity, at some point, it has to cross the y-axis. And so sometimes the intercept is just that spot, right? It doesn't mean anything. It's not useful information. It just happens to be the anchor for our line on the y-axis. And so sometimes the intercept is an extrapolation. So it doesn't give us any useful information. It's not meaningful. Which means it does not provide any meaningful information. Yeah. So like I said, sometimes I'll get you to find the intercept, interpret the intercept, and then as a follow-up, I ask, is it meaningful? Is the intercept meaningful? What would you have to play around with then? You'd have to argue one way or another. Let's go back to the definition or the interpretation of the intercept, right? It's the predicted value of y when X is 0. And so if I ask you if it's meaningful, you would argue, can X be 0 or not reasonably, right? One of the easiest ways to argue it is, no, X is not in the range of our data. And so in this case, no, it's not meaningful. Just logically, would a state have 0% high school grads reasonably, right? What are some assumptions we're making, right? Or would state that kids are still going to high school, that's important. But also if they have some other system, right, then they would have 0% high school grads, and it's not a good predictor anymore. But in our case, right, the percentage of high school grads is between 75 and 95. And so a state with 0% high school grads is not meaningful. Okay. So we could ask, is the intercept meaningful? I'll say argue whether x equals 0 is meaningful. Oops. Is really what you want to do. I could be convinced, right? If you tell me that, yep, 0% high school grads, that's useful information. Sure, right? It has to hinge on x being 0. But besides that, you have somewhat free range. In this case, since the percent high school grads ranges between 75 to 95, a state with 0% high school grads is not meaningful. Or I'll say predicting the percent poverty for a state with 0% high school grads is not meaningful. Should I do it? Throw in the word. Since it is an extrapolation. I hope you hear that in your head. Since it is an extrapolation. I snuck it in there. You don't have to, but it kind of seals the deal. All right. Nice. So it's all what we did is summarized on the next few slides. So I'm going to zip through them. They calculate the slope. They interpret the slope. We already did that. They calculate the intercept. They use the rounded value for the slope. We get a slightly different value. That's okay. I'm not concerned about that. And if we look at our data, right, roughly 75 to 95. And then here we are, at some point it crosses the y-axis, but it's not useful information, right? And so this shows that what the intercept looks like. And we already interpreted the intercept. Yeah. We already talked about it, extrapolation, blah, 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 blah. And then here, now we're back to just showing the range of our data, right? And the percentage in poverties, they use 64.68. I think we had 69. And minus 0.62 times the percentage of high school grads. And that is this line that we have on here. We interpreted the intercept. We interpreted the slope already. It's almost like I've done this before. Our goal for fitting this line was, of course, to make predictions, right? That's what we established very early on. And so now what we would do, right, is we would take this value of x. I wish they would say what it is, 82 maybe, just judging by here. So then we would put in that value of x, and from the line, right, that will give us the corresponding y hat, the predicted value of y. And that's our best guess at what it would be, right? What the predicted percent in poverty would be. And so, right, we can use this line to predict any value, using any value of x, right? We could use it for 20, but once we reach a certain point, 75 here, it becomes very unreliable, right? And so just as an example of extrapolation, and I think it's kind of a funny, the response variable is kind of a funny thing to collect information on, but the men's age at first marriage, implying there are others, between the 1900s or pre-1900s, all the way up to, I'm going to hazard a guess, roughly 1945-ish, right? We have this strong, let's say, roughly kind of 1945-ish, I suspect, right? Up until that point, we have a very strong negative linear relationship. And so it makes sense to use this line, this least squares regression line, to make predictions, but only inside this range of the years, the X value, right? And so past 1945, okay, so it keeps doing a reasonable job. And then we had a plummet, right? And what if you tried to keep using this line? So this line is the predicted values, the predicted men's age at first marriage. Right here, it starts doing a terrible job. And then if I used it here in the 80s, let's say in the 80s here, my prediction would be probably like 12 years old, when in fact it was up closer to 24 or whatever, right? And so it does a great job here, but using the same line for future values doesn't make sense, right? Unreliable predictions. Each of these sections, right? Notice that there's three colors, kind of hard to see, but here it's blue, here it's green, and here it's red. Each of these, we could fit individual models for each of these, and we could make a piecewise function to kind of cobble this thing together, right? If the years are up to 1945, use this linear model. After 1945 to 1975-ish, use this nonlinear model, right? Looks nonlinear to me. And then after 1975, you can go ahead and use this strong positive linear model probably, right? So you can do that, but the caution is to use the line outside. And sometimes, so the reason we emphasize this so much is because a lot of the time when we analyze data, we don't have that background, that kind of internal information about variables, right? And so the beauty with stats is once you learn the tools, you can apply them to biology, you can apply them to finance, you can apply them to anything really, HR stuff, you can apply them to any field, right? And so that's fun, but often we head into kind of a consulting situation where we don't know things about the variables. It doesn't matter, we don't need to know about them, right? All we need are, we know how to analyze them, and then we leave it to the boss man to figure it out, right? So sometimes we have this built-in knowledge, right? Maybe not like this, but if I told you, okay, I found that the heights of children between the ages of 0 and 15 is a strong positive linear relationship, that sounds reasonable, right? What if you have something, so that would look something like, so if we have height here, and if we have age here, 0, I don't know, when do you stop growing? Did I cut them off too soon? 15? I don't know. I don't remember. Let's go with it. You start at some height. And our data showed the strong positive linear relationship, right? You could use that line, but what's the problem? Well, when they're 30, your predicted height would be probably something like 10 feet tall. That's crazy. Why would, but we know that, right? We have that stopping mechanism that says, oh, actually, I know that at some point we kind of stop growing, right? And it plateaus and we have that internal mechanism that says, oh, I shouldn't use the line there, right? But that's not always going to be the case. In fact, that's rarely the case where we have that stopping mechanism. So just in general, you only use the line for predictions inside the range of the x's that you've used. Here's kind of a wild example of extrapolation from the BBC of all places. Women may outsprint men by 2156. Wow, crazy. Okay, where are they getting this from? Just nuts. Women sprinters are closing the gap on men and may one day overtake them. Well, so here's the winning Olympic 100-meter sprint times for men in blue and women in red. How predictable. But we have data up until looks like maybe the 2012 Olympics, maybe 1996, I can't tell. 2012, okay, let's say. And so winning times, the tricky part about race times is that a lower time is better, right? It means you're faster. And so here we have the lower times and the slightly higher times, although this is in seconds. So, I mean, I'd be happy with either. I think be happy up here. Right? And so we've got this strong negative linear relationship, which means that in general, both genders are improving as the years go on. I'm kind of confused why that would be, but because they're just legs, but whatever. They're just legs. Grew them myself. But anyways, maybe, I don't know, technology helps. I don't understand why we're getting faster, but whatever. Shoes. No, I don't know. Doesn't matter. So here, what have they done? We only have data between, I guess the 1900s up to some 2012, let's say. So here we have this strong negative linear relationship, and we've got this very useful line, but only for years in this range. And so what they've done is they've extended the lines, and here at 2156, these lines cross. Oh boy, and that's what they built a whole article around, and that's crazy. Why? Well, if you had to guess, what do you think these boundaries are around the lines? We know about confidence intervals, right? And so for each point here, right, there's some confidence interval around that. I suspect that these are actually prediction intervals, but we don't cover that in this course. They're basically the same. So here, right, I have these bounds on how confident I am in how this line behaves at this point. So notice how quite tight around the data, right? But then as I move out further and further, these lines get wider and wider to indicate that, hey, I'm actually not that confident in this prediction anymore. And by the time you reach down here, and even here, it's just a total mess because we don't know what's going to happen down there. So kind of a fun, bless you, kind of a fun, well, not so fun because it was published and I'm sure people believed it, but fake news. Anyways, just kind of crazy, but that's extrapolation in action. Okay. It's very common. So if you've read any sort of research papers or really any sort of kind of academic article, they usually report the R squared value And so the R squared value is a goodness of fit measure. Okay, we've heard that goodness of fit before for the chi-squareds, and so we use that quite a bit, but it's really just how well does this line fit our data, right? And so R squared, really the takeaway for R squared is the higher the better. R squared is between 0 and 1, and so that makes it a percentage, and so the higher percentage, the better the fit. And so here, comparing this R squared for the men, 88.2% is better than 78.9%, but 78.9 is still quite good, right? Depending on the data that you have, you might be pleased with something like 60%, especially in biology where things are so variable. Whereas if you're doing clinical trials, you might want something a little bit higher before you make any recommendations. So it just depends on what field you're in. So R squared is the strength of the fit of a linear model. Okay? And so we use capital R squared, they had a lowercase r squared, and R squared is just the correlation squared. Okay? And so here, R squared is lowercase r squared. And I suspect that's the reason that they use a capital R for the correlation in the textbook. But, well, there's a couple of other reasons. But so the R squared is the correlation squared. Now, if we think about the correlation, back to the correlation for a sec, the correlations between -1 and 1, what happens when I square these values, right? R squared is going to go and be a positive version between 0 and 1. And so R squared, how do I do this? R squared is between 0 and 1. R squared is a percentage. It's a proportion because it's between 0 and 1, but usually we report it as a percentage. But then if we have to do any math with it, we convert it to a proportion again. And we're used to doing that. Okay. This is the brief definition of the R squared, but I'm going to give you the full definition, and that's what you can expect to see if you have to use it. And so the R squared tells us what percent of variability in the response variable, which is your Y, is explained by the model. And so before we give the full definition, the remainder of that variability, so the variability is the fluctuation, right? And so it's essentially how much of that activity has been captured by this line or could be captured by this line. Now, there's always outside forces, right? So it's very hard to capture all of that variability. And so the remainder is explained by variables that are not in our model, right? Or just randomness, right, in the data. There's an error here, -0.75. 5625, I think. I don't know that, but I did it just mere hours ago, so. Whee, I'm a hero. It is 0.5625. They accidentally use the slope, I think, but that's wrong. So that would be confusing. Yikes. And so for us, R squared is the percentage or the proportion. They're the same, right? We've got those two linked up in our minds, right? And so R squared is the percentage or the proportion of variability in Y explained by the least squares regression line on X. Explained by the least squares regression line okay. This is a long definition and it's, kind of confusing. I know that. But as long as you latch on to the percentage of variability, right? And then your brain just goes, oh, that's R squared, right? You don't even need to keep reading, right? Because as long as you link percentage of variability to the R squared, then you're fine, right? So in this example, the R squared is 0.5625. You take your correlation and you square it. And so 56.25% of the variability. Oh, I guess this should say is the percentage of, yeah, it's okay. 56.25% of the variability in percent poverty, right? Of course, the Y is replaced with what the Y is, and the X is replaced with what the X is. Of the variability in percent poverty is explained by the least squares regression line on percentage of high school grads. Okay, that's fine. How would we use this? What if I wanted to throw a curveball? I've been saying, okay, you'll need the correlation one way or another. And so what could I say? I could tell you that 56.25% of the variability in percent poverty is explained by the least squares regression line. And then what if I asked you to find the correlation, right? And so you could use this, I give you R squared, and then you have to find the correlation. I'm going to insert a page here. Wait, here. What I want to do is I just want to steal from up here instead, maybe. Copy. So I'll say another way that I could give you the correlation, right? You need the correlation to find the slope and therefore the intercept, right? And so one of the ways that kind of sneakily I could give you the correlation is by making you calculate it. And so another way I could give you the correlation is by, wait. Is by giving you the R squared and asking you to calculate the correlation, is by giving you R squared and asking you to calculate the correlation. For some reason, when I said that, it made me think of Notting Hill, I think it is. Asking you to calculate the correlation. what would it look like in this case? Let's focus on this lower one. Whoops, the higher r squared. Whoops, I didn't mean to draw on that. There, this higher r squared. Let's use this one. So, as an example, it might look like this. 88.2% of the variability in male running times or winning times of the variability because this r squared is only for the male running times, so that's why I'm going to specify. 88.2% of the variability in male winning times is explained by the least squares regression line on year, which is your x variable, which I cut out of this little snippet, but that's okay. So find the correlation or calculate the correlation. Okay. So whenever we do math, right, r squared is 0.882, right? And so I'll make a note here, need to convert the percentage to a proportion. Need a proportion. But we're used to that now at this point, right? We report percentages because our brains do really well with percentages. But then for the math aspect, we usually convert to a proportion. Now, the correlation, which I use a lowercase r, and if you use a capital R, that's fine. The correlation is the square root of r squared, which is the square root of 0.882. The pickle with square roots is I could have a negative value, and if I square it, it becomes positive, and I could have a positive value, and if I square it, it's still positive. And so when I undo it, I have the plus minus, right? So when we take the square root, right, to get back to the r squared, I could give it the negative version or the positive version. And so what this means is that r is plus minus, and I'll just do it here, the square root of 0.882 is roughly 0.9391. I'll just call it there. Now we need to pick the appropriate sign, right? We need to pick the appropriate sign. That's the sneaky part of having you find the correlation from the r squared, because then I would need to give you the scatter plot, right? And from here, we see that we have a negative relationship, which has to be reflected in our correlation. And so we have a negative relationship. And maybe I'll do right? This is a negative relationship. Oops, I wrote over my R. There. Therefore, R must be negative 0.9391. Right? That negative, like we said at the very beginning, is important because when I calculate, I'm going to erase this later, but when I calculate the slope, it's R times SY over SX. The standard deviations are always positive, so the only way that I can get a negative slope, which is what I need, is through the correlation. And so that's why it's so important. I'll delete that though. All right. Okay. So kind of two ways that I could give you the correlation. I tell you what it is explicitly, or the alternative is I tell you what the R squared is, and you have to catch from the definition, right? But also the layout of the question. If I'm asking you to find the correlation, I should probably give you something that you can use to find the correlation. So it has to be R squared. So this is the alternative way that I could give you the correlation, something to be prepared for. All right. If I don't make you do this, what do you think I'll make you do instead? Yes, I will, I promise. But also I'll make you calculate R squared, right? As one of the last questions usually. So this would have to be among the first few questions, right? Because you need the correlation to find the slope and find the intercept, blah, blah, blah. If I haven't made you do that, then it would be at the end. Now, what percentage of variability is explained by, in Y is explained by the least squares regression line on X? Then you'd have to know to calculate the R squared. It's a little, that's an easier question, I think. But you can handle this, I know you can. Okay. So this has errors, and we also just did it, so I'm gonna skip it, but it is this one. Okay, how am I doing for time? Oh boy. Okay, that's okay. I just want to mention it. So on the final exam, we will have a numerical explanatory variable, but we could have a categorical explanatory variable. I'm not going to do that to you. Once you're used to it, it is easier, but it's the getting used to it part that's tricky. Okay, and so what if we wanted to consider a categorical explanatory variable? The response variable has to be numerical in order for us to fit a line to it, or at least use the tools that we've been using. But we said at the beginning, okay, the explanatory variable could be numerical or it could be categorical. And when it's categorical, it would look like this. The predicted poverty is still the response. And we get 11.17 plus 0.38, which is our slope still. But then whether it's west or east, which are the two categories for the region. And so this is what we call a dummy variable. And so if the region is east, then west is off. You let west be 0 because if it's east, it's not west, right? And so what would that look like? The predicted percentage in poverty in an east region is 11.17 plus 0.38 times 0. Easy enough, right? And so that's going to be the predicted percentage in poverty for an eastern region. If the region is west, then if the region is west, then west is going to be 1. We turn it on, right? If the west is on, then of course the east is off. It can only be one of the two. So then the predicted poverty for a western state, I guess, is 11.17 plus 0.38 times 1. Right? The math is easier, right? It's either on or off, but a little bit tricky from where we're coming from. Okay, and so whatever the intercept value is called the reference level. You don't need to remember that, but it's good to know. Okay, and so depending on if the west is on or off, right, that'll give us the two different predicted values. And with my last few moments, what if we have 4 regions? Each of these would be a dummy variable, right? And so one of these, when all the other ones are off, would be the reference level, right? And so this is the first time that we're seeing output like this, and that's where we're going to pick up next week, just to wrap things up, see some output. You'll see it in the lab if you do lab 10, but have a look at this and try to see if you can figure it out. But I'll leave that with you. If you have any questions, let me know. Otherwise, enjoy your weekend. Heading into the last week of classes. Oh my gosh.